about countable sets, right? So recall, oh, orange. All right, we're still using orange from last time. Some more countable and uncountable. So recall, a countable set. Anyone remember what the definition is of a set that's countable?
It has to be a subset of following.
Subset of what?
The V.
Oh, Z. So we mostly talked about N. I mean, you could deal with Z also. So a subset of the integers or the natural numbers definitely is countable, but the definition was a little bit more general than that. There's things that aren't subsets that are still countable. Gary, do you have?
This is what I have my notes here.
Okay.
Set up like a bijective with
Right.
a subset of it, like basically giving everything a number, and if you can give everything
Right.
a number, that's countable.
Right. Right, exactly. So a countable set is one that has a bijection to a subset right? And we wrote it, we could also think of it as a list. We could also think of it as the ability to write a program that will print out all the elements of the set one by one and eventually get to any elements you want, right? So we kind of drew it. Let's do it this way. Here's n. 0, 1, 2, 3, 4, 5. And here's our set A, you know, whatever these things are, elements of our set, we can match them up with natural numbers like this. And if we can do that, then it counts. And so I think last time, I mean, obviously the natural numbers themselves are countable because we can match them up with themselves. But we also saw that the set of all integers is countable, even though maybe at first glance it seems like you can't because it's infinite in both directions. Right? But we saw that, well, if we kind of list the integers in a clever order, like if we kind of go back and forth between positive and negative, and actually, I mean, there's lots of, you could do like, list 5 positives and then a negative, and then keep doing that. I mean, that would work too. There's lots of things that would work. We just kind of have to do the positives and negatives both at the same time. So I want to think about some more sets today and think about whether they are countable or not. So, next example. Right, and I hinted slash threatened before that, right, the fact that we're giving this concept a name means there must be some things that are not countable. Otherwise, why would we bother naming it if everything is that, right? So, what about the set n cross n? So the Cartesian product of n. So what is this set, right? Remember, this is the set of all pairs of natural numbers, right? So it would be like, you know, it has like 0, 0 in there. It also has like, you know, 2, 7. It has, you know, 18, comma 4, like 2,497, and, you know, 2 to the 63rd. Right? There's a lot of elements in this set. They all look like pairs of natural numbers. Or we could draw it kind of like this. We could think about having here's 0, 0. Oops. Here's 0, 1, 0, 2. So one way to think about this set, and maybe I'll put like giant set brackets around it, right? I don't know. We could think about organizing the elements of a set like this in this big kind of 2D grid, right? Where the numbers in the pair kind of would be the coordinates of that element, right? So this is definitely an infinite set. Is it countable or not? What do you all think? So is this countable? So I want you to find a neighbor or two and discuss this. See if you can agree or at least raise some interesting questions. Like, what would it mean for this to be countable? How would we show that it is, or how would we show that it isn't? And just intuitively, what do you think? Is it countable or not?
I think it's countable, because all you have to do is you have to order in a way such that every the whole matrix can be untangled into a line. And so one way to do that is if you just draw a diagonal. Eventually, you should be able to get as long as this is like square, right? You should be able to get a line that goes through all of these kind of in a diagonal way. So I started like, say to start like this, and go over here, and go over here, and then like something like that. It's not perfect, but it's not as long as it's square, that should generally fold out, and then we can untangle it, and then we can make a correspondence.
All right. Any thoughts?
That's my idea. That's why.
Let's take a vote first. You have to vote. Okay, everyone has to vote. It doesn't matter if you're right. Just you have to choose. Okay. How many people think it is countable? All right. How many people think it is not countable? Okay, it's pretty evenly split, actually. Nice. So, any thoughts? Why either you think it is or it is not countable? Okay.
Well, like it's hard to copy because, you know, it's the same issue with the integers that we just go off in one direction, you're never gonna like run out. And
Right.
in the same way as something solves out, it's just going back and forth on the number line, positive to negative, but there are a whole lot more directions.
Yeah, that's, yeah. Good, yeah. So maybe you have more to say, but let's pause there and just make sure we're all on the same page. So, this definitely seems harder, or like more infinite in some sense than the integers, right? So the problem with integers, right, that initially we said, well, we can't, what wouldn't work is to say, first list all the positive numbers and then list all the negative ones. That doesn't work because you would never get finished listing the positive ones, you would never get around to listing the negative ones, right? But we said, we can make it work by like going back and forth, right? It's less clear how that same kind of thing would work. We can't, like, there's nothing to go back and forth between, like, so we can't say, first list all the things in the first row, then list all the things in the second row. That's not going to work. There's infinitely many things in the first row. We would never get done with that. But you could say, oh, like, go back and forth between the first and the second row. I mean, okay, that, now you get 2 rows, but, yeah. Okay, so that, I mean, that's not, none of that is a proof of anything, right? It's just like, it seems maybe more difficult to see that it would be countable, if indeed it is, than the other thing. Were you gonna say something else, Garrett?
Yeah, I was going to say, like, if we go with the idea that, like we're saying, even if it's a complex way of counting it, if we have like a computer program type thing that would count it,
Right.
then it still counts. And I'm just thinking here like some kind of like snake thing that kind of follows the diagonal or something
Okay.
along those lines.
Okay, so you wanna like, list them like in a, like start with 0, 0, and then where would I go after that?
Like, I'm just trying to come up with this on the fly, but it seems like each of the diagonals add up to the same number. Like it starts with 0 and then 1 and 2
Okay.
and 3, because you know, at each point like 3, 0, the spot next to it or the spot below it is still going to be like, if you add the two numbers together, 1 greater. And so to that extent, you can just generate a pair and add it to a number. You can get every single one of the numbers on each diagonal and just it would take a long computing power. It would take, you know, forever.
Right.
I think you would hit every ordered pair in this sense.
Okay.
And you just arbitrarily choose to start from like the leftmost number is largest, and then decrease it by 1, decrease the next one by 1. You can get
So you mean, okay, you're kind of saying like, start with this one first, and then like, then do these, like if we're gonna list them, right? Because one way we can say that it is countable is showing like an order that we can list them, where we're gonna get everything in the list, right? So you're saying, like next to all these ones on this diagonal, that where the 2 things add up to 1, and then next do all the ones on this diagonal, oops, I'll erase them. Do all the ones on this diagonal that add up to 2, and all the ones on this diagonal like that, and so on. What do y'all think? Is that gonna work? Yeah? This is not, yeah. I agree, this works. So, maybe if you squint, you can see that it seems similar to how we were dealing with the integers, but it's not quite as, it's not just like going back and forth between 2 things. You know, think of it like, we're gonna list the top row, but like in between, we're gonna do some other stuff, you know, and then come back to the top row, but we do kind of more stuff each time or something. Or you could just think, look, this is a way to, like for any given sum, you know, like this diagonal is like all the things that add up to 4. There's only finitely many things that add up to a certain number, right? Okay, so like 500, right? There's only finitely many of these pairs that will add up to 500. And so if I list them in that order, you know, if any particular pair that I want, like 2000, like this one, you know, this one here, it's somewhere way the heck, I mean, it's kind of far down this way, and it's like way the heck far that way, but like, I'm gonna get there eventually. Eventually I'll get to the diagonal that has that on it, and I'm gonna list it, because every single diagonal is only a finite size. So I will eventually get there. So, yes. And this, I mean, this might be surprising, right? Because you look at this at first, and you're like, okay, no way, because like, this is like 2D. It's infinite in like 2 different directions. How could you possibly turn that into a single list? Turns out that you can. And this was actually surprising, like when mathematicians are first investigating these ideas of infinity and comparing sizes of things, like people kind of intuitively thought that it would be, might be different, like that n cross n would be have a different size than n, but it turns out they're the same. And that was kind of surprising. So, this is perhaps surprising. I mean, at least, it was certainly surprising to me the first time I saw it. I think this is like one of those things where, you know, our normal everyday lives don't prepare us well for having intuition about this kind of thing, right? This seems way bigger than the natural numbers, but we're saying in some sense, it's actually the same size, even though it kind of feels bigger to us. Okay? What about, here's another example. What about D cross E? Okay, so here, this is like, you know, I've got 0, 0 in the middle here, and here's like 1, 0, you know, 0, 1, 1, 1. But like I've also got, you know, here I've got like negative 1, 0. That just kind of goes out, you know, in every direction. So what do y'all think? Is this countable or not? So let's quick have a vote. Just not based on whether you think you have a proof or not. Just like, what do you feel you think the answer is going to be? Given what we've talked about so far, what do you think? Who thinks it is going to be countable? Who thinks no? This one's not going to be countable. Not everyone voted. Okay. Well, any thoughts on how would we? Well, let's start with, if you think it is countable, how would you argue that? We haven't really talked about how to show something is not countable. So it's not clear how we would do that yet, but we definitely know how to show that something is countable. So any thoughts on how you would do that? What do you think it is? Garrett, what do you think?
We try to establish a relationship between like the natural numbers are countable and the integers are countable in a sense, and then show how that can be scaled up to
Okay.
the product.
So maybe reuse some of the stuff that we've done before. Like, we already know that the integers are countable because we have a way to match them up with natural numbers. So maybe we could use that here. Are you raising your hand?
I'm just trying to articulate how to put this. I guess we could like take the similar idea that we did for the Cartesian pair of all natural numbers, and we can start at 0, 0, and then we can kind of like, in a way, make a pattern, a circular pattern that goes wraps around all pairs in a certain area and expand outwards.
Oh, cool. Okay, so you want to make like a spiral kind of
Yeah.
thing? What do y'all think? Would that, so if I go like this, and start listing them in that order, would that get me everything? Yeah, I think so. So this is countable. And there's two ways we can see that. So, well, there's lots of ways. Here's one way, right? One way is you can just look at it and be like, here's a specific pattern that will work. We'll get a list. Garrett, were you going to get another idea?
Yeah, I had another idea. In this what I was saying before about like natural numbers and integers.
Yeah.
What we did that was by after each integer we checked to see if there was a negative version of it. And so here we can just do the like diagonals that we were doing before with natural numbers, and after each one we do the negative version of that. So that's just hit like the opposite side. No, but it wouldn't hit the.
Yeah, you have to be a little careful there. If I'm just doing like diagonals here, I could like maybe do like, you know, 4 different versions of each diagonal. Yeah. The other thing we could just say, look, Z cross Z. I can say how there's going to be a bijection to N cross N. And there's a little detail you have to work out here, which we haven't talked about, which is, well, if I know that there's a bijection from Z to N, then can I make that into a bijection between Z cross Z and N cross N? And the answer is yes. Like you just, you know, given a pair of integers, I just do the bijection to both of them, and I get, you know, 2 different natural numbers. I can just like kind of independently put those bijections together. And then N cross N, we know there's a bijection to N. And in a sense, it doesn't matter what these do. I can just say, look, I know that I have this, and I know that I have this, so if I put them together, again, this is something we haven't proved formally, but I think actually that one is on a module to prove that. But that, if I can like chain two bijections together, and I still, the whole thing is a bijection. So that would show me how to start with any pair of integers and turn that into a pair of natural numbers, and then turn that into a single natural number. And I could go backwards, right? I could do the same thing in reverse. So that would be a way to say, here's some previous things we already know, I'm just going to put them together, and I'm not really even thinking about a picture. I'm just saying, I know there's a way to do this. And yeah, if you made me, I could like go and work out what the details would be, but there is a way to do this. Yeah.
I sort of think because when you actually put in a module per se, rather than like showing that it's A as bisection B,
Yes.
as bisection C,
Yep.
then A to C
Exactly.
also works.
Yeah, exactly. Yep. That's exactly what this is doing, right? Yep. Okay. So, what about, let's just say n cross n cross n. Now, what does that mean? Well, you can imagine just kind of putting parentheses somewhere, right? It means you have like, this is a set of a bunch of pairs, and then you pair those with more numbers. So you end up with kind of like a set of like 3 numbers together, right? So this is really like a 3D cube. I'm not going to draw it because this thing is 2D that I'm drawing on. So, but you can imagine like 0, 0, 0 is at one corner, and then it like goes off to infinity in 3 different dimensions, right? And each thing in here is a triple of numbers that gives you the coordinates, right? Is that counting? You don't think? Grace is nodding. Why do you say yes, Grace? Okay, you just feel like it should be. Yeah, you're right. Yeah. Yes. Right. We could argue that. I mean, you could again. You could give some kind of geometric intuition about what order we can list things. And you could be like, well, I've got this 3D infinite cube. I'm gonna like take like kind of diagonal slices through the cube, like cutting off the corner, and like each one is gonna give me like this kind of triangular thing of numbers, and I'm gonna do those like by diagonal or something. Or you could just say, look, first I could say, n cross n cross n. I could take like this pair of numbers and first use the bijection to turn that into a single number. And then I could do it again, to turn that into the whole thing into a single number. There's a lot of different ways to see this. But the point is, we can keep doing cross n, cross n, cross n, cross n as long as we want, and it's still always going to be counted. Okay?
Can you show us an example of that?
I will look at there, yes. Indeed. So Grace wants to see an example of something that is not countable. So let's talk about the rational numbers. Right, so this is like, the set of all fractions, right? And let's think about this for a second. So here's a number line. Here's a 0. Here's 1. 2, 3, right? So these are like the natural numbers. And like rational numbers, I mean, these numbers are rational numbers, but I've also got a bunch of rational numbers in between, right? So for example, here's like a half. Here's a half, right? Well, there's also like, here's like 3/4. There's like, 2/3 is in there somewhere. There's like 31/32. 1/32, and here's 2. Are there more rational numbers in between these? Sure, right? For, like, I could just take their average, for example, right? If I just add them and divide by 2, I'll get something, which is like right here. I don't know what that would be, right? Or I could take, like, 1/3 of the way along, or 5/7 of the way along. So, like, there's actually going to be infinitely many rational numbers in there. And I could, like, pick 2 really close together rational numbers, like this one and this one, and I could zoom way in, and, like, maybe this is like, 297, over, 543, and this is like 298 over 543. There's still infinitely many rational numbers in between there, right? Because, again, I could just, like, take, any fraction of the way along between these numbers is itself a rational number. So, right, so here we started out with just the natural numbers, 0, 1, 2, 3, 4. But now we're saying, look, the rational numbers, like, anywhere you zoom in, there's infinitely many. You can zoom in as far as you want, and there's always infinitely many in between, anywhere, right? So it seems like there's way more rational numbers than there are natural numbers, because, like, the natural numbers are looking pretty sparse. Right? I've just got, like, 1, 2, and there's, like, infinitely many rational numbers in between, right, from 1 to 2. So it's like infinitely fuzzy fuzz. I mean, not every number is rational, right? There's places on here that aren't rational. So it's not just, like, everywhere, but there are infinitely many of them. So what do you all think? Are the rational numbers countable or not? See some shaking heads.
How would you be able to divide the entire have to go down and up to, like, be able to do that?
Yeah, how would you actually be able to list them all? I mean, if definitely if I, like, okay, well, this half is like the first one, and then, like, 2/3, but I already missed a lot, right? So, like, okay, no, not 2/3, like, this one right here, that's the second one. And then, oh, whoops, I missed infinitely many, shoot. Right, so maybe intuitively I can't make a list of them. Garrett, what do you think?
If we have some way of, like, getting numbers in some way that is, like, going to fit every number eventually, just like I ran through, but, like, what I'm thinking of is, like, the digits of pi. They're random and never repeat. Doesn't that mean they're going to hit every single digit eventually? And so to that extent, you just take patterns from it, you will.
So you're like, okay, just list pi, and then you'll interpret it as rational numbers or something. So that's very interesting. So pi in particular, actually, it's unknown whether it is random. Like, everyone thinks it is, and of course, what do you mean by random? I mean, there's various technical things where you could say, well, it means that every possible thing occurs somewhere in there, like, eventually, or that's actually unknown. Like, everyone thinks that's true, but we don't know. What was that?
I think I'm actually okay then.
Yeah, but maybe you could pick some other number that we know that does that or something. I don't know. But you think maybe there is a way to list all of so, like, we do eventually hit every rational number? Maybe?
Probably not.
Probably not. Okay.
I imagine part of the people that make it have the exact same thought I did, and if this is still thought to be accountable, then I see that wrong.
Right. Argument by there are smarter people than me, so therefore. Yeah. So, any other thoughts?
I think Mary does first North Giggle.
Only the first? Oh, that's good.
Congratulations.
Yeah, right.
Unachievable goal.
Okay, so, I have to admit, I definitely set you up. I described this in such a way that made it sound uncountable. But, what is a rational number? Rational numbers is the set of, A over B, where A is, and B are both integers. And also B is not zero. some way we can define it. What is that? That's just a pair of integers. It's a pair of integers. We already said the pairs of integers is countable. Right? So Q, the rationals we could like match up with pairs of integers. And we already know, or sorry, pairs of integers. And we already know that we can match that up with them. So if this fact that Z cross Z is countable, if that didn't weird you out before, it should now. Right? Because like, yeah, it blows my mind. But yes, it is true. Between any two natural numbers, there's infinite many rational numbers, but still there's the same number of them. Now, part of it is, what's obscuring it is that like, well, what we could not do is give a list of all the rational numbers that are in order on the number line. That doesn't work, right? For exactly the reason we were talking about. You have to use a different order that doesn't correspond to like their order on the number line. But it is possible. So one way you could do it is just like, you know, go by diagonals and just like, now some of the diagonal things like 2, 2, that's the same, 2 over 2 is the same as 1 over 1. So you just skip that one maybe, right? You could just go by diagonals and just like skip the ones that you've already seen, the ones that aren't relatively prime. And you could list all the rationals that way. It turns out there are other ways to list the rationals that have some really beautiful properties that are not just like going by diagonals. Yeah, so, yes. That's kind of crazy. Okay. So enough teasing here. What about set of real numbers? Okay, so this is like, we could think of this as like finite or any number with finite or infinite decimal expansion. I don't want to like actually try to formally define for you what the real numbers are, because actually to really formally define it is very tricky. But we can just think of it as, you know, 2.39846 open, like it just goes on forever. It might not be a rational number, but that counts as a real number. Like pi, right? There's no fraction that's equal to pi, but we can put it, you know, at a specific point on the number line, right? So, you know, just think of it as like, you know, everything on the whole number line. The entire number line. So is that set countable? It turns out it is not. And, you know, at this point, again, so I said the fact that we're calling this something, it seems to imply that there's some things that aren't countable. But from looking at these examples, you might be forgiven for thinking, no, maybe everything is countable. Like there's any set, there's always some clever way that you can like list everything in the set and, you know, give like number everything in the set, right? I mean, if something is infinite, that just means it goes on forever. So does that mean you could just like list them and, you know, give each one a number? Well, people used to think that. But it turns out, no, there's actually different sizes of infinity. There's some infinities that are more infinite than others. And that's the case here. So the real numbers are actually much more infinite than the natural numbers or the rational numbers. There is no way we can't put them in a list. There's too many to put in a list. So, and I will, yeah, we have time. I will prove it to you. Okay, so it turns out that R is not countable. Okay, so how would we prove that something is not countable? So let's use our superpower, right? Let's just write down what the definition of being countable is. We'll negate it, and then we'll kind of like see what we get. And that'll tell us how we can prove it. Okay, so, how to prove this? So if I say not countable, so for some set A, what is the definition of being countable? The definition of being countable is there exists some f, which is a function from natural numbers to A, such that f is a bijection. Right? That's what the definition is. Okay, so I can just, so this is the same as for all f not bijection. Yeah. Okay, well, what does it mean for f to be a bijection? It means it is injective and surjective, or one-to-one and onto. So I can expand that out. So all n. Okay. Not injective. Okay, and then we'll do one more. We'll do De Morgan's law here. So this is for all function f from n to a. F is not injective, or f is not surjective. Okay, and usually, so how do we prove something is not countable? Somehow we have to say first, well, suppose I have some arbitrary function from natural numbers to my set A. Well, a function from the natural numbers to A, right, it gives us, for each natural number, it gives us a particular element of A. And so that's really just, we can think of that as a list, right? What's the 0th element of A? What's the first element of A? What's the second element of A? So I can also think of this as saying, suppose I have an arbitrary list of things in A, right? Well, I have to show then either that function is not injective, meaning there's some duplicates in my list, or it's not surjective, that means there's something that got left out of my list. Okay, so, wow, that is, i.e., for an arbitrary list of elements of A, either there are duplicates or something is left out. Now, the duplicates thing is not very useful because typically, if we're going to say we have a list of things in A, I mean, it's not hard to avoid having duplicates. I mean, I guess, if A is finite, then, yeah, you have to have duplicates because if I'm making an infinite list, I'm going to have to repeat myself. So that's stupid. We know for sure finite sets are not, finite sets are countable, so that doesn't really. So typically we focus on this. If we say, suppose I have a list of everything, or suppose I have a list of elements of A, and it doesn't matter what that list is, I can show that there's something that got left out, at least one thing that got left out. If I can show that no matter what list I have, there's always something left out, then it's not possible to have a function that's a bijection to the natural numbers, because I'm always going to leave things out. There's too many things in A to list them all. Right? So this is what we're going to focus on. Okay? So, let me do. So suppose we have an arbitrary list of real numbers. Okay, actually gonna just focus on, real numbers between 0 and 1. So, like, if that's uncountable, then surely all of real numbers is also uncountable, right? Stupidly. So, let's just focus on, you know, R such that 0 is less than, or I'll say R is a real number, and 0 is less than R is less than 1. Actually, you know what, I'll just say less than or equal to. We can include 0, 1, that's not counted. So it's always going to be 0 point something, right? So 0 point, but I don't know what it is, right? It could be anything. And I can't assume what this is. I'm just saying I have some list. But I can say, well, it's got some digits, right? And we'll call this one D00, D01, D02, D03, dot, dot, dot. And it's okay if it's finite, because I could just say all the digits after that are 0. So if my number is actually like 1/4, I can say 0.25000000 forever. Okay? And then I've got my, you know, number R1, which is some other digits. So we'll call this D10, D11, D12, D13, dot, dot, dot. Here's R2, D20, D21, D22, D23, dot, 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 and so on. Okay? This is an infinite list because it's supposed to represent a function from the natural numbers to the real numbers, right? So I've just got kind of a numbered list of real numbers. And what we need to show is, no matter what this list is, there's some real number that's not on the list. Okay? So we must show the list is incomplete. Some real number is not in the list. Okay, everyone, does that make sense? Because that would show that this function from the natural numbers to real numbers is not, it's not onto, it's not surjective, right? It leaves out some things. Well, here's what I'm going to do. I'm going to show you, I'm going to describe for you a real number in such a way that it's not going to be on the list. So, create a real number, 0 point, we'll call it, you know, C0, C1, C2, C3, such that, well, how am I going to pick C0? I'm going to look at this digit here. And I just want to make sure that C0 is not the same as D00. I don't care what it is. Look, D00, it turns out that digit is 2, maybe, right? That first number, R0, is 0.2 something, something, something. I can pick whatever digit I want as long as it's not 2. Okay, and then I'm going to pick C1, and I'm going to make sure that C1 is different than D11. You can probably see where this is going, right? C2, how am I going to pick that? I can pick it to be anything I want as long as it's different than D22. Okay, so C2 is not equal to D22. No, dot, 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 Cj is not equal to Dj2. Okay? And I claim this real number is not anywhere in this list. Why is that? Well, can this number be equal to R0? No, because they start with different digits. Right? I picked this number, C0, so it's not equal to this, so they can't be the same. Right? Well, can this number be R1? No, because they have different second digits. Can it be equal to R2? No, because I picked them so they have different third digits, right? So every single number on this list, this number is different somewhere, right? So there's some digit where they could be like, all the other digits might happen to be the same, but at least that digit is different, so they can't be equal. Okay, so them in at least one decimal place. So this is called Cantor's diagonal argument. It turns out to be a really fundamental pattern that shows up a lot. And actually, we saw diagonals in several contexts today, right? When showing that something was countable, we could do it by diagonals. And also, there's like, this is the diagonal we're talking about here. You like look at this diagonal here, we just like pick something that's different from every single thing along that diagonal, and that ensures that it's not on the list. There's a few like little gotchas about, oh, you know how like you know, like 0.499999 forever is really the same as 0.5, and like to really make this completely formal, you have to deal with that stuff, but the idea still works. There's just like, it's just the tedious details to really make it really formal, but this is basically it. So this is surprising, right, that there is actually this set, the real numbers, there's so many real numbers that we cannot actually list them all, right? So there's more, the real numbers are more infinite than the natural numbers. And you might ask, does it stop there? Is it just like two levels of infinity, right? There's like the natural numbers kind of infinity, and then there's the real numbers kind of infinity. What do y'all think?
There's probably infinite.
Of course, there's infinitely many infinities, yes, exactly. There are. All right, we're out of time. Have a good weekend. I will see you all Monday.